from all over the world, and wherever you may be viewing me, perhaps in the afternoon, I say good afternoon. If it is in the morning, I say good morning. And if it is in the evening, I say good evening to you. This moment, I want to quickly look through a topic in chemistry, and that topic is transition elements, metals or the force transition series. Now, when you talk about transition elements, what exactly are we talking about? We are talking about elements that have partially filled 3D orbitals. Element with partially filled 3D orbital. What that means is this, that their 3D orbitals are not completely filled. Remember, we have four types of orbitals. We have the s orbital, the p orbital, the d orbital, and the f orbitals. So the d orbitals are the transition elements, and element with partially filled d orbital, d orbitals. And this set of elements we are referring to here, they are located in the periodic table between group 2 and group 3. They lie between group 2 and group 3 of the periodic table, and they are in three rows. They are in three rows. So the first row is what I'm considering this moment, which is regarded as the first transition series. The second rows are referred to as the second transition series, while the third row are referred to as the third transition series. In any case, these are metals. Now, to start with, we want to look at these elements that are referred to as transition elements. They are from number 21 in the periodic table to number 30. You are aware that we have the first 20 elements which we have been exposed to in our previous classes, particularly from the earlier of SS1 class. So you have been taught we have the first 20 elements. Now you are not expected to learn more about these elements, at least from the 21 element to the 30th element. And this element we are referring to here, they are referred to as the transition elements. The 21 here is scandium. We have scandium be the 21 element. We have titanium be the transition, the 22nd. We have vanadium as the 23rd. We have chromium as the 24th. We have manganese as the 25th. We have iron as the 26th. We have cobalt as the 27th. We have nickel as the 28th. We have copper as the 29th. And we have zinc as the 30th element. All of these elements, they have their own symbols. For scandium, its symbol is SC. For titanium, is Ti. For vanadium, is V. For chromium, it is Cr. For manganese, it is Mn. For iron, it is Fe. For cobalt, it is C small letter O. And for nickel, it is Ni. For copper, it is Cu. For zinc, it is Zn. And each of these transition elements, they have their electronic configuration. Now, I start with scandium. The electronic configuration of scandium is 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, 4s2. Now, something will come to mind here. From what you have been taught in the way to write electronic configuration, you are aware that usually 4s will come before 3d. But here we are talking about a series, transition series, and we are seeing 3d coming before the 4s. I'll give a little explanation thereafter after now. Now I go to the 22nd. Titanium is the number 22, and it's the configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d2, and 4s2. And we have vanadium, number 23, 1s2, 2s2, 2p6, 3s2, 3p6, 3d3, and 4s2. We have for chromium, 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, and 4s1. And we have for manganese, 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s2. For iron, we have 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, and 4s2. For cobalt, 1s2, 2s2, 3p6, 3s2, 3s2, 3p6, 3d7, and we have 4s2. For nickel, we have 1s2, 2s2, 3p6, 3s2, 3p6, 3d8, 4s2. And for copper, we have 1s2, 2s2, 2 pieces, 3s2, 3 pieces, 3d10, 4s1. And for zinc, which is the last one there, we have 1s2, 2s2, 2 pieces, 3s2, 3 pieces, 3d10, 4s2. So these are the configurations or the first transition series as have been highlighted. Like I told us, writing configuration from element number 1, which is hydrogen, to element number 20, which is calcium, we often bring the 4s before the 3d. 4s often come before 3d. Why? Because 4s has a lower energy level than the 3d. However, the gap, the difference in their energy is so very little to an extent that easily electron can be transferred or can be moved without much notice from one orbital to another orbital. I mean, from the 4s to the 3d and from the 3d to the 4s because of the little energy difference between these two orbitals. That is why in this transition element, in writing electron configuration for transition series, the 3d takes priority over the 4s since the energy level is very little compared to each other, and this is what identifies an element as a transition element, the fact that they are d orbitals. So the d orbital here takes priority over the 4s. The more reason why you're having the d coming before the s, because you have to satisfy the d orbital first before you actually cater or satisfy for the completeness of the 4s orbital, as you are going to see in this lesson and discussion for today. Again, you will rightly observe that among these elements that have been listed, you have a trend that have been followed right from scandium all through to vanadium. But getting to chromium, instead of having 3d4, 4s2, you realize that we are having 3d5, 4s1. The 4s that have been completed from scandium here is not complete. It's not having one electron. Why the 3d that is normally should be 4, based on the way we have been arranging it, is now having 5. Why is it so? Because an element of the transition series is most stable when it's either half filled with electron or completely filled with electron. So every means possible to ensure the stability of the 3d orbital is what the element will be looking for. That is why in chromium, instead of having 3d4, 4s2, it is rather arranged in such a way that stability will be enhanced. Now we have 3d5. That is, one electron is removed from the 4s. I told you electron can easily be removed between the two orbitals. So one electron is removed from the 4s and taken or added to the 3d, which was originally 4, making it 5. That is the most stable way this element can be. That is why in writing the configuration for chromium, this is the acceptable way to be written, in which it can be written, because it must be stable. It must, you are working towards stability. So 3d5 as against 3d4, 4s1 as against 4s2. The same thing applies when you come to copper. Copper is atomic number 29, and in its configuration, the 3d normally should have 9 electrons. The 3d should have 9 electrons, while the 4s should have 2 electrons. But because at that level, it is not stable. So a way of getting it stable or making it stable, one electron is removed from the 4s, because I'm telling you that we cater or we consider the d orbitals priority over that of 4s. Now you remove the electron from the 4s and the electron is added to the 3d. The 3d that was originally supposed to be 3d9 is now made 3d10. So we have 3d10, now 4s1. That is the arrangement you have for this electronic configuration of the first transition series. Now, to move on in this discussion, we want to look at the properties of the first transition series. Of course, I told you that they are metals. These elements are all metals, and the usual properties of metals, as we have discussed in our other classes, we realize that metals are sonorous, metals are malleable, they are ductile, they have they have all those properties we have listed under the metals. They are also applicable to the transition metals. So in addition to that, we talk about the metallic bond. The metallic bond in the transition series is stronger than the metallic bond among the group 1 and group 2 elements. You have metals in group 1, in group 2, and in group 3. Now we are talking about another set of metals which are referred to as the transition metals. So the metallic bond in these d orbitals, which is the first transition series, is stronger than those of the s orbital, which are group 1, 2, and 3 orbitals. And that is what occasion the hardness and the hardness and the toughness that is seen in all these elements, because the metallic bond is stronger in them than we have under the normal element, the group 1 and the group 2 metals, which are referred to as S block metals. Now we talk about the chemical properties, of these transition elements. The chemical properties of these transition elements. What exactly do we look at here? We look at the block. In terms of their block, we realize that the S block metals, they have electrons. The S block metals, they have their own electrons. And also the d orbitals, they have electrons. So we see that the nuclei of the transition metals, they exert greater attraction on their electrons. The nucleus of the transition metals has greater attraction on their electrons than we have for the S block orbitals or this S block element. Why is that happening? Because the transition metals, they require greater energy. They require greater energy to remove their electron. I mean, they have greater energy required. They require greater energy to remove their outermost shell electron. The s orbital, they have little electrons in the outermost shell. Therefore, they require a very lower energy. So their initial energy is very low compared with that of the transition, or those of the transition metals. That is the reason why metals of the transition series, they exert greater attraction on their electrons. Now, we talk further and we look at the transition elements. We want to look at their reactivity. In terms of the reactivities of the transition element, the reactivity decreases across the series due to the corresponding increase in the values of the ionization energy. So the reactivities of this transition series, it decreases across the period. You look at it from scandium to zinc, across the period. So their reactivity decreases. You see, that tells you that scandium is most reactive among them compared with zinc, which is the last of this first series, transition series. Now we look again at the magnetic property. We have looked at the reactivity as a chemical property. Now we are looking at the magnetic property of this transition series. Now, transition series or transition elements, they exhibit two or different kind of properties with regards to magnetic properties. Now we talk about diamagnetism. Some of these transition metals, they exhibit diamagnetism. What does that mean? That is, they are repelled by magnetic field. When you talk about diamagnetism, is the ability of a metallic substance to be repelled by a magnetic field. Why? As a result of the paired 3D orbitals. Their 3D orbitals are paired, and once the 3D orbitals are paired, there will be a repellent on the electrons. There will be no attraction towards any other electron because their 3D electrons are paired. So the eagerness to react is not there, unlike those that are having one unpaired or more electrons. That is talking about diamagnetism. Those are the transition elements that are exhibiting diamagnetism. They are repelled by magnetic fields. That is one of the properties exhibited by transition series. Another property related to magnetism that they exhibit is called paramagnetism. Paramagnetism. Paramagnetism means they are attracted towards the magnetic field. They are attracted towards the magnetic field. When you talk about paramagnetism, is the ability of a metallic substance to be attracted towards the magnetic field as a result of the unpaired 3D electrons. So they have some, maybe one or more unpaired 3D electrons. For that reason, they exhibit paramagnetism. That is, they are attracted towards the magnet because of the unpaired electrons. That is a magnetic property. At times, you could look at another property of magnet there, which is ferromagnetism, which is essentially being exhibited by iron as a transition element. Now we further look at other chemical properties of the transition series, which include variable oxidation state. Transition series, they exhibit what we call variable oxidation state. You see, these elements, they show variable oxidation states in their, as a result of their unpaired 3D electrons. Now, for example, you look at manganese. Manganese as a transition metals, as a transition metal or series, is having variable oxidation state. We can see manganese exhibiting a +2 in a compound like MnO. That's manganese 2 oxide. You can see the same manganese exhibiting +4 in a compound like MnO2. That's manganese 4 oxide. You can see the same manganese exhibiting an oxidation state of +6 in an ion or radical such as MnO4 2-. Okay, you can see the same manganese exhibiting the oxidation state of +7 in an element, in a compound or a radical such as MnO4- is exhibiting this variable oxidation state, and that is peculiar to transition metals. They show variable oxidation state, and the reason for that is because of their unpaired 3D electrons. They have unpaired 3D electrons. For that reason, they exhibit variable oxidation state. Aside from that, they also have what the property we refer to as formation of complex ions. These transition metals, they have what we call formation of complex ions. They form complex ions. And when you talk about a complex ion has several, has a central positive ion. A complex ion is an ion that has a central positive ion that is linked to several other atoms, or ions or molecules. And these atoms or molecules or ions that are linked to this central positive ion are called ligands. So when the complex has 6 ligands, they are arranged in an octahedral arrangement. We call it octahedral arrangement when the complex ion has 6 ligands. But if the complex ion has 4 complex ions, when it's having 4 ligands attached to it, it is arranged tetrahedrally. An example of one of the ions or complex ion formed is what we call tetraimine copper 2 ion. Tetraimine copper 2 ion. And we also have hexacyanoferrite 3 ion. These are examples of some of the ions that are formed by transition metals. Another chemical properties that we'll be looking at among is formation of colored compounds. The transition metallic ions, they are usually colored, and this is why also serves as a useful guide in identifying this compound. Each of them, they have their distinct colors, so they form colored ions in compounds, and the colors are associated with a partially filled d orbitals, that is from D1, 3D1 to 3D9. So they exhibit variable or different kinds. And we could see zinc and scandium being an exception. Zinc and scandium, they're having an exception here. They are colorless. And the reason they're colorless is because they do not have partially filled 3D orbitals. They do not have partially filled 3D orbital electrons. They don't have. Zinc is completely filled. Its 3D orbital is completely filled with electron. And for scandium often loses the electron, the outermost shell electron. When it does that, because it will not, that means it doesn't have electron in the 3D orbital. That is why scandium and zinc are usually colorless, while the others that are having from D1 to D9, they are exhibiting color, or they form colored compounds or colored ions. Now we also talk about another chemical property of transition metals, which include catalytic property. Transition metals, they exhibit catalytic activity. And when you talk about a catalyst, what is a catalyst? A catalyst is a substance that alters the rate of a chemical reaction without taking part in that reaction. So most often transition metals are used either as an element in their elemental form or in their compound form. They are used as catalysts. And why are they used as catalysts? Because of their ability, their 3D orbital, because the ability of the fact that they have variable oxidation state, they can exist in different oxidation states. That's one of the reasons why they are used. With the ease with which they can change the oxidation state, enable them to be used as catalyst. And we can see iron is one of the transition metals, is used as a catalyst. Remember the Haber process where we use iron as a catalyst. We also remember the hydrogenation of oil or formation of margarine where we use finally nickel as a catalyst. And some other processes that we have discussed earlier, we see that metals or transition metals are used as catalysts. This is a brief overview of all the transition metals, the first transition series that we are discussing. And I wish to talk about one of these transition metals which is of importance, and that is why I will be going to this part. One of these transition metals which is essential, that is iron. I want to talk about iron. Iron is an element that is often talked about. In fact, is an element or a metal that is the second most abundant metal found in the earth crust. Aluminium is the most abundant metal. After aluminium, it is iron that is second. So iron occurs mostly in their ores. It occurs mostly in their ores, and the most important of these ores of iron is amethyte. Amethyte, that is in pure iron oxide, iron 2 oxide, in pure iron 3 oxide rather, that is amethyte. And we have some other occurrences of iron in their natural form. We talked about amethyte, we talked about magnetite, we talked about magnetite is iron tetraoxide. We talk about FeCO3, which is a iron triazo carbonate 4. Talk about siderite. They are all the different occurrences, the different forms in which we can find iron. Of all of these, various existence or occurrences of iron, the most important of them, or the most form in which iron is found, is amethyte. And that's why in extracting iron, it is often extracted from amethyte as one of the major raw material for that process. Now, because of this iron also that we said is also found in, apart from in the natural form, is also found in combination in hemoglobin, also found in combination in chlorophyll in plants. We have it in all of that. It's a constituent in hemoglobin, and it's a constituent in chlorophyll found in plant. Now, because iron is found in its ore, and when we talk about ore, is the natural occurrence of minerals in the earth crust. And in that form, they contain a lot of impurities. They needed to be purified and brought out in their original form. So that is why it is necessary to extract iron. And in the extraction of iron, we have major raw materials that are used in extracting iron. One of those raw materials is the amethyte. The amethyte is a major raw material. We have coke, it's another raw material, and we have limestone. These are three major raw materials that are used in the extraction of irons. Now we look at them. How do we go about the extraction of iron? The extraction of iron is actually carried out in the blast furnace. In a blast furnace. Now, a blast furnace is a very huge setup where this process or processes are carried out. Now, right in the blast furnace consists of high temperature. The lower part, the higher part. The lower part consists of a temperature around 2000 degrees Celsius, while the higher part, the upper part, the top of the furnace is around 200 degrees Celsius. Now, from the top part, the upper part of the furnace, we have these raw materials mixed together, and they are poured in from the top. mix together and pour into, the coke, the limestone, and also the amethyte. The iron is first roasted to remove the impurity, first to remove the literal impurity before it is mixed with coke and also the limestone, which are now introduced into the blast furnace right from the top. Now, at the bottom of the furnace, we have a part that is called the tuyères. The tuyères. In that tuyères, we put a very hot air is blown from the tuyère into the furnace. Now, as that occurs, I told you the temperature below and the temperature above. As that occurs, we have series of reaction that will begin to occur in that furnace. The first thing that will happen is that the hot air, the carbon dioxide, the oxygen gas in the hot air, and coupled with the flame, the furnace, and the oxygen in the furnace will combine first with the coke, which is one of the raw material that was introduced into the blast furnace. So the oxygen from the hot air blown into the furnace will combine with the coke. And once that happens, carbon combining with oxygen, carbon is the coke we're talking about here, carbon combining with oxygen is giving us carbon 4 oxide, Now, in this area, we talk about carbon 4 oxide. When the carbon 4 oxide is formed, the carbon 4 oxide form immediately, we again react with the coke. The carbon 4 oxide form will again be reacted with the coke inside the same blast furnace, and the coke will then reduce the carbon 4 oxide to carbon 2 oxide, that is CO. Once the CO is produced, that CO will then combine with the amethyte, Fe2O3. We combine with the amethyte to liberate the iron from its various component or constituents where it is found to be linked to. So at this point in time, we have liberated the iron from the other components. The limestone that was also part of the raw material used for this process, at this high temperature will decompose. The reason for the limestone is to be able to remove the various impurities from the process or the process of the extraction. So the limestone will decompose. When the limestone decomposes, it produces calcium oxide and CO2. The calcium oxide produced at this point in time will then combine with an impurity, which is sand, silicon 4 oxide, that is found as an impurity. So the calcium oxide will combine with the silicon 4 oxide in that process and form calcium triososilicate 4. So to form calcium triososilicate 4, the calcium triososilicate 4 is known as slag, which is an impurity during this extraction of iron. Now, the iron, after you have removed the slag, of course, in the furnace, the iron immediately will get down into the bottom. We have the molten iron floating on top of the impurity. We have the impurity there. We also have the molten iron there. So in that process, we form our iron. So the iron sinks down inside the furnace, while the calcium triososilicate 4, which is the slag, will float on top. So as the iron is sinking down at the bottom, it is then collected or allowed to be run into molds where it is then collected. Now, the form of iron that is produced at this point is known as the pig iron. The pig iron is what you get from the extraction of iron from the blast furnace. Now, further purification of the pig iron, that is removing further some of the impurities in this pig iron, like the carbon content in it, then we give you what we call the cast iron. And when you further purify the cast iron, you obtain what you refer to as the wrought iron. Now you will see that in this diagram that I'm about to show to you. You see, in the diagram that I'm about to show to you, you see the diagram for the blast furnace. That is the blast furnace right there, and the various processes that are involved at every stage of the extraction. Now, like I told you, that we have different types of iron. ranging from the first that is extracted, that is gotten from the extraction, which is the pig iron. And after further purification, we have the cast iron, and the purest form of iron that can be gotten is the wrought iron. All of these ions, they have their own different peculiarities, they have their own different usage, and we look at them. The pig iron is very hard. That is one of its property, very hard and very brittle, and because of that, its uses or its use is limited in industrial setup because it's very hard and it's brittle. So that is for pig iron. It's limited in usage. Now we talk about the cast iron. The cast iron does not require high tensile strength, and thus it is used for substances like cooker, like stove, like radiator. It's used in making the lamp post. It's used in making the railings. It's used in making the base of Bunsen burners. It's used in making every machinery. So cast iron is used to make all of that. Now, when the iron is now purified to the purer form of iron, which is the wrought iron, because this purer form of iron is very soft, is very tough, and is very malleable. And because of these properties, unique properties of it, is then being used to make substances like nails, something like chains, like iron rods and iron sheets, and the horseshoe, agricultural implement, and some other core and the cores of a magnet. So these are some of the usage of iron, the different forms of iron as we have seen. I want to believe with this discussion of mine today with you, I want to believe you have learned a lot. And I want to commend your effort in listening to this lesson for this period. I want to believe you have been blessed. And if you do have question or any interaction, feel free to give it over or give the admiration in the comment box, as you can see. I want to thank you so much for viewing. Happy listening. God bless you.